Alright guys, welcome back to another lecture in the series for the gas laws. We've already gone over the simple gas laws at this point and the importance of units that we're going to be using within the gas law chapter. So today we're going to take a look at the ideal gas law itself. We're going to learn a little bit about where it comes from, so specifically the R constant and where we get that from, and then we're going to do some practice as usual so that you guys know how to properly solve using the ideal gas law. So let's get started. Last time we talked about the ideal gas law and how it comes from or is derived from three of the simple gas laws, which includes Boyle's law, Charles' law, and Avogadro's law. So if you need to refresh your memory on that, go back and watch the other video. These all come together to give us PV equals nRT as the ideal gas law. And what that's telling us is that pressure times volume of a gas is equal to the moles of that gas times the gas constant times T for temperature. Now, I also told you in the last video that the value of R is 0.08206 or 0.0821 for those of you that round it. That's completely fine. We want to talk about the units of R and where R comes from. So R is that constant that we find prevalent in all of the simple gas laws. But here we have more pieces moving. The T and the N are moving along with the P and the V. So before we were holding two of the units constant and then two others we would play around and manipulate with. And when we get ready to solve for R is derived, it's a constant, and it has to come from a specific set of units if it's always going to be a given value. And R actually can change. You can change it when you're dealing with energy calculations and you replace joules, in place of some of the pressure measurements and other things. But for right now, we're going to focus on the fact that R has certain measurements when we're measuring gases with the ideal gas law. And the units that are required for pressure, we're going to need ATM. So let's keep track of this. Pressure is ATM. The volume we will need in liters. N is moles, and moles within itself is a unit, so we'll just keep moles down there. And then temperature. So we've got pressure, ATMs, volume in liters, moles, which is represented by N, is just moles, and then the temperature is going to be in Kelvin. So when we do this and we try to solve for R, we're going to determine R based on what's called the standard values or the standard state. So if you go back to the first lecture on units, you'll remember that we talk about STP, which is standard temperature and pressure. And if you remember that, the standard temperature is 0 degrees Celsius, or 273.15 Kelvin. The pressure would be 1 ATM. That's the standard, 760 millimeters of mercury if you're going through these different units. The volume is going to be liters, and the value for the volume, we've talked about it in the previous lessons, but Avogadro found that a single mole, 1 mole, of any gas fills up 22.4 liters when we're at standard temperature and pressure. So we have standard values for each of these and we can solve for R. Pressure is going to be 1 ATM. The volume is going to be 22.4 liters. That will be equal to 1 mole R. And then the temperature is going to be 273.15. And that's from 0 Celsius. You add 273.15 to 0, you get 273.15 as Kelvin. And so if you take 22.4, the ones drop out. If you take 22.4 divided by 273.15, you get R. And this is the number that you should be getting out of the calculator. Because we set these units ahead of time, when you are doing the ideal gas law, you have to have your individual variables in these given units. Because R is always going to be this value right here when we use the ideal gas law, and R has ATM, liters, moles, and Kelvin built into it. And in fact, the unit for R is ATM times liter over mole times Kelvin. And sometimes you'll see ATM times liter times inverse mole times inverse Kelvin. The inverse is 1 over mole and 1 over Kelvin, which we are representing here. So R is really going to have this unit right here, ATM times liter over mole times Kelvin. And that's where we derive R from when we solve for the ideal gas law using those standard values. So let's go ahead and actually practice some ideal gas problems using the ideal gas equation. So we'll start with this one here. It says how many grams, and notice that it asks for grams, of oxygen are there in a 50-liter tank at 21 degrees Celsius when the pressure is 15.7 ATMs. So that's a lot of information that they're giving us there. And what we need to do is we need to start by saying, okay, what am I searching for? I have a volume, 50 liters. I have a temperature, 21 degrees Celsius. And I have a pressure at 15.7 ATM. Now, if I want grams, I'm going to have to first solve for moles. And I can get moles from the ideal gas equation, and then I can convert those moles to grams using the periodic table. So hopefully that thought process makes sense to you guys as you're looking at this. So let's go ahead and attempt to solve this. So first of all, the pressure. Is the pressure okay? Yes, it's in ATMs. And we said, if we go back here, ATM, liter, moles, and Kelvin. Those are the units we need. So keep those in mind, jot them down somewhere as we're practicing through this. So PV equals nRT. The P is good to go. We have 15.7 ATMs. Now, the volume. Is the volume good to go? Yes, because it's in liters. If it was in milliliters or some other unit, I would have to change that. I've got 50.0 equals, I'm going to solve for N, so I have PV equals N, that's going to be the moles, R, which I'll put 0.08206 here, and then don't forget I also have to multiply through by my temperature. Now, the temperature is 21 degrees Celsius. Now, Celsius is not what we're looking for. If you go back here and you look, we need Kelvin for the temperature because that's what's built in to our gas constant, R. So in order to get that, I'm going to need to take 294, I'm sorry, I just said the answer. I'm going to have to take my Celsius, which is 21, and add it to 273.15, and that will come out to 294.15. So 294.15. So once I have this, I'm going to take 15.7 times 50, and then I'm also on the other side going to take 0.08206 times 294.15. I will divide through by the right side over on the left side, and I will solve for N. So I'll give you a minute to do that. And hopefully, when you solve for N, N is going to equal 32.5 moles of O2. Because we're dealing with oxygen, which elemental oxygen is O2. So 32.5 moles of O2. We're not quite done yet, but that's a good step. We want to get to grams of O2. So what I would do is I would bring this down here and I'd say 32.5 moles of O2. And I'm going to convert this using the periodic table. So I want to get rid of moles. 1 mole of O2. If I look up oxygen on the periodic table, it's 16. That's its weight in grams per mole. I have 2 oxygens. So I'm going for 32 grams of oxygen in every 1 mole of oxygen. The moles will cancel out. You're going to take 32.5 times 32 grams. And what you should end up with in proper significant figures and scientific notation is 1.04 times 10 to the third grams. Now, it's 3 significant figures. Well, actually, the way that I wrote this, I should probably have a 0 here, because that's only 2 significant figures for the temperature. But if I have 50.0, 21.0, and 15.7, then I would have 3 significant figures. All right? If not, if I only had 21, then that would mean that it is 1.0 times 10 to the third. So remember your significant figures while you're doing this. But that would be the answer. All right, a cylinder contains 91.3 grams of nitrogen gas. If the volume of the cylinder is 8.58 liters, what is the pressure of the nitrogen gas if the temperature is 21 degrees Celsius? Right? So, and again, let's make this 21.0 degrees Celsius, just so we have 3 sig figs that we can work with. Okay? So when you get ready to start this one, you should notice you're looking for pressure. So we're going to look for our P in the PV equals nRT. The V, the volume, is already given to us in liters, so that's good to go. 8.58, which is equal to, now, N. The N is going to be a little more complicated. We have grams of N2, so we're going to need to convert into moles of N2. So we'll take 91.3 grams of N2, and I want to convert that. So when I go to convert that, I'm going to need, for every 1 mole of N2, if I go to the periodic table, it's 14.01 for every nitrogen. I have 2 of them as elemental nitrogen, diatomic. And so 28.02 grams of N2, grams will cancel, will give me the moles of N2. And so when I'm doing this, if I take 91.3 and divide by 28, I should get 3.26 moles of N2. And so that's what I'll put up for the moles. 3.26. Hopefully you guys realized how we got to that. Okay, R is our 0.08206. And then we also need our temperature. It's 21.0, just like the last problem. So if you add 273.15 to 21, you'll end up with 294.15 Kelvin for your temperature. All right. So let's erase our nitrogen work down here so we leave enough space. So while I'm doing this, why don't you guys go ahead and solve for P. So what you're going to need to do is multiply the moles times the gas constant times the temperature. And then once you get that value, you will need to divide through by the volume, and that should give you your pressure in atmospheres. So take another minute and do that. All right, so pressure is going to be equal to, if you multiply the right side all the way through each of those 3 variables, you should get approximately 78.7. And then if we come through and we divide by 8.58, which is the liters, the volume, that'll give us the pressure. So hopefully you end up with the pressure at 9.17 ATMs. Again, 3 sig figs. I increased the temperature. I said let's do 21.0 instead of just 21. So we could keep 3 sig figs at the end here. So that's ATM, atmospheres. Alright, so this is how the ideal gas law works. You need to get into those specific units. A lot of times you'll be given Celsius. You need to get into Kelvin. You should remember that your R is 0.08206 and has specific units of atmosphere times liter over mole times Kelvin. And other than that, that's pretty well how the ideal gas law works. So thanks again for watching. Please like the video if it was helpful. You can comment if you have any questions or want to leave comments and feedback. And as always, please subscribe so that you know when the latest videos come out. Thanks, guys.